Hello everyone, we are Team Light, guarding the truth. Our mission is to identify the images generated by TTI, guard the truth, and identify the falsehood. With the rapid development of artificial intelligence technology, the pictures generated by text-to-image model are becoming more and more difficult to distinguish. This is a collection of real and fake picture generated by TTI. Can you identify which picture is real and which is fake with your own eyes? Can you capture the subtle differences between real and fake? Obviously, this is a difficult task for ordinary people like us. So we found a pair of eyes that can replace us to distinguish between real and fake, which is the conventional neural network. It simulates the process of human eyes recognizing image features and the human brain processing features for classification. But it can do what a human cannot do, capture image patterns at a higher dimension and identify subtle difference between real and fake. Our baseline model is the pre-trained DenseNet 121, which is a conventional neural network model trained on the ImageNet dataset. In our reference lab, it perfectly completes the task of classifying style-generated images and real images.
Therefore, we used the transfer learning method to enable the pre-trained DenseNet model to apply the knowledge originally learned in ImageNet to our TTI and real image binary classification tasks. In order to allow the transfer learning model to learn more image features, we generalized and enhanced both the real and fake datasets. We not only applied common data augmentation methods such as cropping and scaling, but more importantly, we expanded the types of images in the dataset. Our dataset includes not only human face, but also other real-world objects such as cars and animals. Our model ultimately successfully achieved 90% classification accuracy on the test set. The precision, recall, and F1 score for both classes, fake and real, remained consistent at approximately 90%, indicating a well-balanced performance across both categories. Our trained CNN model can reveal the previous truth for us. Not only that, due to the application of the sigmoid activation function in the classification layer, our model can also indicate the probability that the input image is real, providing confidence information for people who use our model to detect images.
We have achieved relatively good model performance. This is far from enough. We also need to consider the robustness of the model. For example, a new challenge is what if we suffer a white box attack? We found a method from some researchers. It's called ensemble model. We used the method to develop a new model. It remains our CNN ability to extract features, but replaces a random forest classifier as a shield in the classification layer. This shield makes the white box attack method based on backpropagation gradient perturbation ineffective. There are two main advantages of our ensemble model. By replacing the final classification layer of a CNN with a random forest, the model becomes non-differentiable, which does not allow gradient to be calculated. thus nullify the effectiveness of gradient-based attack methods. Random forest as a classifier. This method is less sensitive to specific data distribution and is more robust against overfitting compared to traditional single decision trees, making it difficult for attackers to generate a small perturbation that can consistently fool the model. And the performance of our ensemble model after training showed a high accuracy, with both validation and test accuracy reaching around 86%. The precise, recall, and F1 score for both classes remains consistent, indicating a well-balanced performance across both categories. A challenge comes from another attack method, black ball attack. If someone generates adversarial samples that may confuse the model, whether our model can resist such an attack. We simulated a black box attack method called adversarial stickers, which was proved to be able to physically interfere with the model in a black box environment, especially the DNN model for imagery recognition tasks. To test the robustness of our model under this attack method, we applied two types of stickers, a beard or a funny monkey, to our human face dataset. However, our test results on adversarial samples showed that both our models, pure CNN and ensemble model, has shown good robustness, especially our CNN model.
To further enhance the security of the model, we integrated an anomaly detection model into the model. By analyzing the age density in the imaging, we are able to identify possible imaging tampering or adversarial examples. If the anomaly detection system detects an anomaly in the imaging, it will refuse further processing of the images. This design effectively prevents potential adversarial samples from entering the model, thereby avoiding possible adversarial attacks before the image enters the classification process. This method not only improves the recognition rate of adversarial examples, but also reduces the cost of the model processing adversarial examples. By targeting DenseNet 121 structure optimization, data enhancement, transfer learning, adversarial defense, and anomaly detection, our model exhibits stronger generalization capabilities and robustness in the task of classifying real and AI-generated images. Compared with the baseline model, the improved model not only achieved higher accuracy on multiple test sets, but also provide effective defense in the face of complex adversarial attacks. The introduction of the anomaly detection model further improves the security of the model, allowing it to refuse to process this image before potential adversarial attacks reach the classification layer, providing a more robust protection mechanism. The above is the research result of our team. Thank you for listening.